Hi, how's it going? So I want to just preface this video by saying that this system, this multi-threaded system, isn't quite working optimally. And I'm happy to put myself in the stocks as a village idiot and say, hey, I gave it a go. There are better ways to do this, definitely. But I'm just going to go ahead and present it anyway, because I am going to be going with this system. I mean, it doesn't make things that much worse than it was running before, but I'm running off on a big tangent. So the idea is that things like loading meshes and loading images and stuff, wouldn't it be great if we could just send that off to another thread, load that in the background, and do a bunch of those at the same time? In practice, it doesn't quite work that way, but in principle, it does. So let's go ahead and set this up. The first thing I want to do is I want to just get the system working on a single thread, but using the same sort of system, like a job allocation system that we would use with multi-threading. So I'll just go ahead and make a new folder, and I'll call that VK job. It's not exclusively Vulkan jobs, but anyway. And then I'll add 2 new source files. There we go. Okay, so we'll start with the header. Okay, so I'm just importing a bunch of these, including a bunch of these headers, because, well, the 2 major jobs we've got are loading meshes and loading images, and so we need to know about those object definitions. Okay, so it pretty much is what it looks like. For each job, it's going to have a status variable, which will take one of these values. So we'll have a job class, and this will be an abstract class. Okay, so the job is going to be in a linked list, because we're going to have a queue, and we need a quick way to determine like the next job, the next job, the next job, as well as add a whole bunch of them. Of course, we're going to have a status, and by default that'll always be incomplete. And then we'll have this virtual function. So all we need to do is specify a command buffer and a queue, and then say do the job, and the job has its own. Each instantiation of the class has its own function for performing the job. So the 2 jobs we're going to take are basically making models and making textures. So I'll just grab a bunch of those. So we have this make model, which publicly inherits from the job class. And then, well, you know, the question is, what do we need to make a model? Well, we need a whole bunch of info. So there we have it. We need to specify all this information, which we were already specifying in the past when we were loading models. But in addition to that, we also need to pass a reference to the mesh which we want to populate with all of the data, if that makes sense. So what we'll do is we'll have the constructor. There we go. Okay. So then we can just specify that, yeah, this is the actual definition point for this function. Okay, great. So now I'm not sure if I've done this already, so I'll just quickly check back. But basically, I want to set this up so that the object mesh, have I done that? Not quite. Okay, so I'm just going to change this so that instead of the constructor, because at this point, when we make an object mesh, it automatically gets loaded by the constructor. Instead of that, what I want to do is defer the loading by shifting this not have it loading in the constructor, but just have a custom load function that we can call at any point. So I'll just call that load, and I'll go back here and I'll just change this to the load function. There we go. Okay. It might complain that, yeah, it's fine. All right. So we've got that so far. Now I'm just going to go over to the header, the CPP, the source file, and get that set up. Okay, so this is a little bit of a funky thing. I don't know if I've really talked about this, but in C++, when your class has a reference to an object, and then you're passing in a reference here in your constructor, like that needs to be initialized, and you can't initialize it in the body of the function. That needs to be done before that. So if we hover over here, it says provides no initializer for the reference member. So for instance, we would be saying something like this mesh equals mesh. That would be initializing it, but C++ still doesn't like that. And the way we get around this is something called initialize lists. So before the body of the function, we can just put this little colon, and then what this will essentially do is set some values before even calling the body of the function, and that's just what we need. So what we'll do is just go mesh and then initialize that with the value of mesh. Seems a little funky, but that solves the issue, and then we can pop in here and say, okay, well, this is being recognized as the parameter, and then this one is a data field within our class. So we are properly setting that up. Okay, but otherwise we can just keep going. Okay, so get ready for the magic. Now here's the execute function. So we'll go okay, we've got that one there. Excellent. So I mean, this is very straightforward, because now our object mesh has a load function, and we have a reference to the object mesh that we're talking about. So we can just go mesh load and then pass in all that info. Okay, so once that function completes, we can set our status to complete. Okay, so I like to just run things every now and then just to check that it's working. So what I'll do is I'll just head back to the engine, and then right down here, luckily the error shows it up for us. And I'm going to mess this around a little bit. So I want to actually declare everything before I start loading. So I'll say, okay, that's the meshes. Now we'll declare the materials. And I'm actually going to, yeah, okay, this will just take 1 second. Yep, so I will declare the file names up first, and then I'll declare I'll make the descriptor pool. Okay, so we have the descriptor pool created there for the mesh objects. Now just go down and grab this texture info, and I'm going to be a little dodgy. I probably don't have to do this, but I'm going to declare texture info down here and also up here. So yeah, it's a little dodgy that I'm redeclaring the same texture info, but it's scoped to the loop. I could have done it a different way, but let's do it this way. Okay, so this is a little weird. What I'm going to do is just unify this all together. So I'm just going to make a vector of all the object types that I'm going to be working with. And that sets it up so that I can loop through those. So I can say for okay, so I can access the underlying file name right there, and then I'll just change this to type. Now what is this? This is model file names based on the type, and the first of those, oh, right, I'm just really messing this up. So what I'm going to do is I'm going to create an object mesh first of all, and then I'm going to consume it. So those are the two different bits. Because when this goes multi-threaded, that job of loading the file will be a separate job. We'll have to queue that up. And in order to do that, I'm going to need a set of these. Okay, cool. So I'll just insert a blank model there. And then at this point, I'll load it. Okay, cool. So then we have the object file name, the material file name, which will be the second bit of that vector of file names up above. And then the pre-transforms, which again will be indexed by that mesh type. Okay, cool. So now we want to consume this, and we will say, okay, its index is that type. The vertices, well, we'll access them by the unordered map, and same with the indices. Okay, so I'll just give that a go. There we go. Okay, great. It's working. It's doing what we expect. So I'm going to leave that. Okay. And okay, now I'm going to do the same thing with the textures because we're constructing a texture. Let's set it up so that we are loading it as well. So go to the image, texture, and I'll just change this constructor to a load function. And the same over here. So I'll say, all right, that's the load function. All right, then we'll go back to the engine and say, okay, well, let's make the texture and then we'll load the texture. Give that a go. Yeah, okay, perfect. So again, really nothing unexpected here. All I've done is rename a function, but we're setting it up so that these things can be called separate to the constructors. Okay, so I think I've beat about the bush enough here. I'm just going to finish off the rest of the job system. So we've got this make model job. The other job I'm going to have is a make texture job. And in order to make a texture, we're going to need that texture info. And we're also going to need we could use a reference, but I mean, really, over here we're dealing with pointers, so we'll just make it a pointer. Okay, great. So for our constructor, we'll just take, all of this info. Now let's go ahead and define that in the source file. We're not dealing with any references here, so it's fine just to copy over. Okay, so for the execute function, look, the execute function above didn't use the command buffer in queue. I guess we didn't need that, but yeah, because I'm just thinking, because the object mesh doesn't actually communicate with the Vulkan buffer. It just loads stuff into memory. We didn't need it, but in this case, we are going to need these. So remember that the texture info, whoops, where are we? Yeah, the texture info does use a command buffer in queue because the texture creation job involves various asset creations, which happen on the graphics card. So what I'm going to do is I'm going to say, okay, get the texture info, set its command buffer and queue to the input of the function, and then go ahead and call it. And this is what's going to enable multiple threads to create multiple images at the same time, because each thread will have its own command buffer. Okay, so what am I missing? We just need to set the job to complete. Okay, cool. So that is a job that will make a texture. Then the question is, how do we coordinate all of this? So I'm going to make another class, which I'll just call a work queue. The reason I'm keeping track of both the first and the first so that I can iterate from the start to the end, and the last so that when I add a job I can just add it at the end. I mean, it doesn't make a big difference, but that's fine. Alright, so I'll have a function, actually change my mind. I don't really need this length variable, but just in case I use it in future, let's have it anyway. So then we have some functions. First of all, we want to be able to add a job to the queue. Then we might want to be able to get the next job, and then we want to be able to clear the queue. There we have it. Excellent. So let's go and implement those. Right, okay, so what we're doing essentially is just popping on this pointer to the end of the queue and increasing the count by 1. Alright, so as for getting the next job, we want to look through and find the first job which has a status which isn't completed or which is pending. There we go. Okay, cool. So we've got nothing on the queue, we've got nothing. Otherwise, keep looking through. And this is just checking. When we reach the end, this will be set to null pointer, which will fail the test. But basically, we just find the first thing which is pending, and if everything else fails, then yeah, we got nothing. Okay, now as for clearing the queue, go through here. All right, so this is just iterating through step by step and deleting each node, basically, and then just resetting the state of the queue. Okay, cool. Right, so then how do we use this? Well, one thing we'll need is we'll need to go to the engine header and import this, and then declare that we're going to have a work queue. So we'll go right down to this asset stuff. Here we are, asset pointers, and say, okay, we have a work queue. Something like that. And then I'll go in and refactor this. So we'll go to the asset creation. And it's this stuff here. So this, I want to, instead of directly calling the function, I want to pop that onto the queue. So there we go. Simple as that. So we pop on, a make texture job and a make model job, and then right down the bottom, before we proceed, we want to basically flush the job, or flush all the jobs. So we'll go get the next job, and then we'll say while there's a valid job. We'll execute it, and for the command buffer, for right now we'll pass in our main command buffer, and of course this will all be happening on the graphics queue. Then we'll get the next one. Okay, great. And then once we get to the end here, we can clear the work queue. Just double checking my own stuff. I think that's fine. The only thing is, now for the texture info, we don't need to specify this stuff because it will be populated in the jobs execute function. So let's just play this, give this a go, see what's happening. There we go. Okay, excellent. It's working. So it's just a small step, but think of it like now we've got a single threaded job system. We popped on a bunch of jobs and then we completed them. So that's good. I'm happy with that for now. No errors. Okay, good stuff. The final stage here is, okay, how do we take this and now create a multi-threaded system? Gonna need a few things. One of those is we'll just go off to our config header and include, include the thread and mutex header. Like I said, this isn't the 100% best way to do it, but it works for now. I'm going to keep it for now and maybe update it in the future. But yeah, okay, thread and mutexes. Then we'll go to the job system, go to the work queue, and I'm going to put in a few things. I'm going to put in a mutex, a mutual excluder, so that only one thread can access the queue at one time. It would be a real nightmare if we didn't have that. And then I'm also going to have, this isn't such a big deal, but just for convenience, I'm going to add just a quick Boolean function just to really do the same thing as get next, but just check if the thing's clear or not. So we can go right down to this one. It's almost the same function. Oh, whoops. Almost the same function as this one. This is just really a quality of life improvement. If we've got nothing on there, well, of course we're done. And now if we see something which is not complete, then we can return false. We're not done. And then if we go right through the end and everything's fine, then yeah, we're done. Okay, excellent. So we have that. Then in addition to that, I'm going to add a new file here, a new class. Okay, so I'm going to use classes for the threads. We're going to need a reference to a shared Boolean, which is going to track whether all of the loading work is done. And then we're going to need a reference to the work queue so that as jobs are put on there, we can check those, grab a job one at a time, and execute it. So then the rest is just boilerplate. Okay, now I think I've talked about this in a past video, but in order to launch a thread on something, I spelled that right? Yep. In order to launch a thread on something, we need the bracket operator so that the std thread library can say, okay, we're going to execute the thread which has been launched. Okay, no worries. Now, as before, we'll use the initializer list. So we'll say initialize those references, and then we'll just save the rest. By the way, this looks a little funky, but the way this works is the bit after operator immediately is the operator that we're working on. So, for instance, if I change that to a plus, then it's a function, it takes the operator, and it takes the things which are either side of the operator, and then the body of the function declares what it is. But in this case, it's just a little funky because the operator itself is a set of brackets. Okay, no problem. So I'll go ahead and just write this. So the first thing we'll do is we'll get access to the work queue, and that's done with the lock function. And the reason I'm just doing this is just initially so I find that doing standard output from multiple threads can get pretty messy, so I'm acquiring a lock in order to do standard output. Yeah. What I could do is wait, but I found that if I waited, it would be messy. So what I'm doing instead is I'm just attempting to grab the lock, and if I fail, then I'll just put the thread to sleep for a little bit, so I'll wait for a while. And yeah, then try again. Yeah, so this will just keep going forever until we tell all the threads to stop. They'll try to grab the lock, so they'll try to get access to the work queue. If another thread is busy with that, they'll just wait for 200 milliseconds and then try again. And hopefully that should be the right sort of load balancing. Like I said, it's not perfect. There are definitely better ways to do it. Like we can have condition variables and make threads notify other threads, but I'll just keep it simple for now, even if that is a little less efficient. Okay, so at this point we've got access to the lock, so our thread is the one thread talking to this work queue. If we get that and then we see that all the jobs sitting on the work queue have actually been completed, no problem at all. Just unlock it, so release access, and then try again. And then, go from there. Okay, now this little check here is just safe checking. I mean, the done function should handle that already, but let's do it anyway, just in case. So what we'll do if we get to this point, and everything's still all completely valid, then I'll just notify the console that yep, the job is being done. And then I'll take the pending job, set its status to in progress, and that will make sure that another thread doesn't grab it. But then what I can do is I can release the queue so another thread can grab another job. And then go ahead and execute it. Okay, cool. So what I'll do then, this will keep looping forever and ever until we signal to the thread that they should be done. So in that case, we'll just say thread done. Okay, cool. So that is basically the worker thread, how it's going to run. Now, I'll just close this down and go to the engine. And we can leave the job. I think the job stuff is fine. We'll just go to the engine header. And we see here we have this make assets. Actually, before I do that, I'm just going to include those threads. And then right down next to the asset stuff, we've got the work queue. Going to need a bit more state here, so we'll have a Boolean variable done, which will be false, and then a vector of threads, which I'll call the workers. And then right down the bottom, we have make assets. I'm going to make 2 more functions. Yeah, so we're going to basically make them and then end them. Now, like I said, it's not a perfect system. So when you make a thread, there is an overhead in launching a thread. So a common pattern, which I might look into in future, is the pool pattern, where a pool just straight up launches all of the threads that it can, and then it keeps them in a holding pattern, so they're sleeping, they're not using CPU time, and then as needed you can spawn a thread by putting it into a working pattern, into an active state, waking it up. But for now I'm just going to keep it simple. So we'll go to the, where are we? Up here, and I'll do this just before I make the assets. Okay, so I'm finding the maximum number of threads that we can sort of launch efficiently, -1 of course, because we have a main thread here. And then I'm just reserving that. Okay, and what I'm also going to need to do is allocate a command buffer for each of them. So I'm going to need to set this one up as well. And this is a little bit cringe because, as you can see, we don't really need swap chain frames, but let's do it anyway. So the way, so I'm going to push this back because it's a vector, push things onto a vector, and then the way I launch a thread is with the thread constructor here, and then I just need to pass in the object which is going to run as the thread. And the way I'll do that is by instantiating a worker thread. Okay, so that's it. At this point, all the threads are pushed on and they are doing their thing. They are constantly looking for jobs to do and stuff. So then right after making the assets, I'm going to end the worker threads. And if this was a more dynamic program, I'd do things differently. But anyway, so we'll just signal to all the threads that we are in fact done. And then of course we don't need to do any of this, but we'll just look through each of these. So in other words, we are waiting for each of these threads to be done. And then we'll just signal and then just get rid of everything. Okay. Okay, excellent. So let me just review the actual asset. Oh, by the way, should go right up the top. Jeez, this is messy. Okay, and then, right, so we'll go, yeah, make the worker threads, make the assets, and then end the worker threads. Okay, right. So what I'll do is I'll just get access to the work queue, submit the work, and then release the work queue so threads can work on it. Okay, so at this point we do our thing, and then, oh, actually, I'll modify this. So then we submit those jobs. It'll actually be 6 jobs because we'll have 3 models, 3 materials. But then we're going to wait for everything to be done. Okay, so just the same as before. Try to grab it, and then what do we do here? We'll test if the queue is done. If it's done, of course, we should clear the queue and then unlock. And of course, we'll need to break out of that infinite loop. And then regardless, I mean, if we get down here, then clearly it's not done. We should still unlock the work queue. Okay. So then by the time we get down here, all the work which was submitted was done by the worker threads. And I'm actually just going to do this on the main thread. Reason being that as we add more assets, well, first of all, it's a little difficult to parallelize this job of consuming stuff. There must be a way to do it, but maybe not. And then this stuff, we're only loading 6 textures. So as the number of materials increases, the number of textures that we load for the sky is still going to be 6. So I'm just going to keep it there. So let's give that a go and see what happens. There we go. Okay. So yeah, I mean, as you can see, we've gone through here. We've allocated a whole bunch of threads. There were 6 jobs, so 6 threads have signaled that they were working on a job, and then everything is done and the threads were ended successfully. Now, this hasn't really sped up the loading time. I suspect that the program is I/O bound, but I also suspect that as the number of assets increases, we'll better be able to utilize the parallelization that's happening here. Fingers crossed, that's my theory at least. So anyway, and just out of curiosity, we've been doing all of this in debug mode. We could do this in release mode, and it would be super quick. There we go, that took about 4 seconds as opposed to 40 seconds, but it's stable. It loaded, it's stable, it's multi-threaded. Anyway, so look, as always, I hope you got something out of this. I know that this isn't the pro implementation of this concept, but I would really love input on how to improve it. Anyway, have a great day, and I'll see you again soon. Bye.